JWST. And it's going to talk about the PAH luminous galaxy.
Okay, hello everyone. I'm Yu Wei from the National China University, and my topic is the polycyclic aromatic hydrocarbon called PAH luminous galaxies in the JWST's early release observational data. So this is my outline. First, I will introduce the PAH and the PAH features in the galaxy's spectra. And next, we will introduce the JWST data and ST fittings. And third is the results of the ST fitting spectrum and the redshift and the luminosity for the PAH galaxies. And finally is the summary of our work. So what is the PAH? And PAH is a chemical group that has thousands of different molecules with the carbon and hydrogens with multi-aromatic rings, and that is the simple PAH molecule. And why we are interested in PAH is that the PAH is everywhere in the universe, and when it is in the star-forming regions, it will absorb the UV and the optical and emit in the infrared. And so it is a good trace for the pH luminosity of the star forming activities. And in the spectrum, the right is the spectrum of the red galaxies. You can see that in the red have the pH molecule in the 6.3, 6.2 and 7.6 have the pH features. And for the distant galaxies, the pH features will shift to the higher wavelengths in the mid-infrared. So we use the James Webb Space Telescope. The mid-infrared instrument have the synthesis images in the mid-infrared. And we use the cosmic evolutionary resistance survey called the CS fields. And there have the 6 bands for many observations, which are from the 7.7 to 21 microns. And this is the images from the JWST series for the 7.7 microns. And we use the source extractors to pick out the gases in the 6 bands of the MIRI's CSP. And so totally there are 300 galaxies and 102 in the 15 microns in the JWST series catalog. And we use the method from 2009 that the pH selected gases have a high flux density ratios larger than 0.8. So in the color part, that the 12 red sources is the pH selected gases. And this is the selected gases images, clear images for the 6 JWST's observation bed. So next we do the gas readings that we use the JWST MIRI 6 bands and match to the other telescope from the optical to the near infrared. So total we have 20 bands from the optical to mid infrared photometry to do the JWST fittings. And also we set the velocity to be the free parameters, so we can estimate velocity and total infrared luminosity. And this is the result of the spectrum of the PAH galaxies. So the purple point is the observational data, and we have the two clear emission line. So first is the blue scatter emission line, and second is the red dust emission light. And we have the clear pH features in the mini tree, and is from 77 to 21. And this image. And this is the other samples of the SD result. And we have the 10 of the 12 pH selected galaxies have a good acidity result with the chi-square smaller than 10. And this is the redshift distributions of 12 pH selected galaxies and others. And for red points type, we have the peak around the redshift 1, and 10 of them are the gas larger than redshift 1. And this is that indicates the pH features is in the 50 microns. And this result for the total infrared luminosities and the peak pH peak luminosity in 7.7 micron. Like the red points is our JWST result, and the green and blue is the previous result from the Hubble telescope. As we can see that our red points is in the one order faint in the total infrared luminosity, and most of them have strong pH emissions. So these 10, the 10 faint and normal galaxies are the star-forming gases that we first see in the world by the JWST. And so next is summary. We use the JWST's mean density ratio to select the pH galaxies, and 10 of them is have the good acidity fittings, and we have the redshift higher than 1, and this is the first time we see these star-forming galaxies. And there's other JWST researches from NTHU Cosmology. Thank you.
Yes.
Can you go to the preview page? And go. Oh, here. Well, how to obtain the right-hand side figure from the left-hand side result?
You mean the left-hand side?
Yeah.
This is the left-hand side figure is just from the JWST's observation result.
How about right-hand side?
Right-hand side is when you put the photometries in the purple point is the different photometry values, and then put it in the signals models, and we can estimate all the spectrum.
All right. I have a further question. Go to the next page. And next, here. Why the red one JWST result, which arrow bar are larger than others?
Or some of the arrow larger since there's no 21 microns detect. So, like in this figure, this one that do not have the 21 values, so we set it for the upper limit, and you will have a large error bar in the estimate the total invariant velocity.
Yes.
Okay, thank you.
For the next question.
Here, hi, good stuff. As we know, JWST still, we're still trying to understand JWST, especially the calibrations and 0 points. Sears is covering a well-known field, it's called EGS. And I was wondering, from a technical point of view, have you checked against your measurements against previous, for example, Spitzer measurements at the similar wavelengths? So you can confirm that your measurements are actually not too off in terms of photometry compared to the Spitzer, which is we know.
We have checked into Spectra.
So there are 2 bands?
Yes.
Okay, so there is no channel 3 and channel 4?
Channel 1 and channel 2.
The only channel 1 and channel 2?
Yes, so it's 3.6 and 4.5.
Right. But that should also cover, near cam should also cover that, right?
You mean the JWST near game?
Yeah, that's right. Or you only use mirroring?
For this early release observation data, that the series, their near camp data observation regions is not covered as the mirrors region.
I see. I see.
So we do not, so in our work, do not have the JWST near camps.
Okay. Cool. The second comment is about the fitting for the SED. So I guess Sears might have 5 for coverage for the field. So in order for, yeah, exactly. So I see that it stopped at 24 micron. So in principle, there's more data available, higher, longer wavebands. So that would allow you to cover better an infrared luminosity, for example. Just a suggestion.
Is it from Herschel?
Yeah, I think so.
They are not, did not detect. These are 100 times fainter.
But they're not blinded catalogs. Deep blinded.
Probably not detected in this. These are 100 times fainter than Spitzer sources.
I see. Okay, so you have checked.
These are JWs, yes.
Okay.
Okay, any more questions? Yeah, good.
Okay, thanks for your presentation, but I'm not sure if I missed something. And I'm curious about how you select this sample. Your sample selection is the flux density, flux ratio higher than 0.8. So, is there any reason that you choose these sources?
So in PAH features that we have this kind of peak for the pH emissions. So that will generate that in the different bands that the colors will have a large gap in the observations.
You mean that the color is, the flux ratio is higher. For those flux ratio higher sources, the emission of pH is stronger.
Yes, it's really.
Okay, thanks.
Okay, let's thank the speaker again. We